Oh yeah, golly. Golly, gee willikers. This unit on stoichiometry and stoichiometry include an aqueous solution. Huge stuff. We could go on for days and days. I have a whole bunch of slides here. I'm going to chop myself off after about, I don't know, 10, 12 minutes and let you look at the rest of the slides if you feel like it. But let me go through a few just for kicks and giggles because stoichiometry is so much fun. Oh, say, if I were writing an equation of N2 plus H2 to NH3 and balance the equation, it should give me some kind of an idea about the stoichiometry involved that I would expect for N2 in reaction with H2. So let me do that. Oh, whoa, wait a second. I need to go like this. I apologize. Here we go. So here's my equation. I wrote N2 plus H2 gives NH3. But then I realized the right-hand side of the equation had 3H. I'm sorry, I recognized the left-hand side had 2 nitrogens, so I figured I better get 2 nitrogens, and that gives me 6 hydrogens, and so 6 hydrogens. Okay, so 3 H2s react with 1 N2. So 1 N2 react with 1, 2, 3 H2s, 1 N2 react with 3 H2s, and I'm out of H2. Dang it. Looks like H2 is a limiting reactant. I've got N2 left over, but in any case, my picture would include this, and oh no, my picture would include 1, 2 NH3s from this, and 2 NH3s from this, and 4 other extra leftover N2s. Although it looks like I was too lazy to draw the picture. But imagine, this one combines with these 3, and this one combines with these 3, and I have 2 NH3s from the purple shading and 2 NH3s from the green shading. Draw it out for yourself if you wanna. Wouldn't be a bad idea. You react chemicals A and B and they make one product. It takes 100 grams of A to react completely with 20 grams of B. So if A and B react completely and they only make one product, wouldn't it be, say, 120 grams by conservation of matter? So I think 9 is E. What's true about the chemical properties of the product? Psh, I don't think you know. That's a kind of a fun, curious, bizarre thing about chemistry. You never know what you're going to get. The properties of the compound are not necessarily and rarely ever related to the properties of the constituent elements. Crazy, but true. You notice that water sometimes drips from the exhaust of your car. Is this evidence that there's at least a small amount of water in the gasoline? I hope not. Man, if you get water in your gas, that's going to screw up your engine big time. No, when you burn stuff, you get carbon dioxide and water. That's a take-home message for the whole semester. Burning things gives carbon dioxide, greenhouse gas, and water vapor, which is not so bad. I wouldn't mind a little more humidity around here. Good for your skin. A new barbecue grill weighs 30 kilograms. You put 3 kilograms of charcoal on the grill. You burn all the charcoal in the grill, and the grill has a mass of 30 grams. What's the mass of the gases given off? 30 kilograms. Huh, that's weird. I don't know. What did I say down here? So I took carbon, oh yeah, charcoal, and burned it completely, if that's possible. Although you know it's not possible because you have some ash left over. But what if it was possible? I took oxygen from the air and carbon from the charcoal, and it makes carbon dioxide gas, and the gas floats away out of the grill, and there's nothing left behind. So I suppose that could be a thought experiment that the mass of the grill before is the same as the mass of the grill afterwards, considering if everything got burned up and taken away into the air. That's a silly one. This is not a silly one. This is a good one. You have an iron bar and it rusts. And it rusts and it rusts. The iron bar rusts. Which of the following is true about the what's the total mass? Consider the iron bar and the balance as iron bar rusts. Does the balance still read 75 grams? Less than 75 grams? More than 75 grams? The balance will read greater than 75 grams, but if the bar is removed, the rust is scraped off, and the bar replaced is still weighs 75 grams. It's a common misconception, because rust is flaky and not dense and falls away, and makes the metal that is left behind weaker. But truth of the matter is the iron combines with oxygen in the air. So if you measure the total mass of the rust from the iron and the beginning amount of iron, it would be more. It gets more massive. So 1 gram of iron yields 1.4 grams of iron oxide, and so indeed it would weigh more, even though it would be damaging to the metal and what we wanted to use it for, because the rust flakes away as weird, it's like light and fluffy, and it's not as strong as the iron itself, but indeed it would weigh more because we're adding oxygen to it. Consider the equation 3A plus B gives C and D. If you react 4 moles of A with 2 moles of B, which is true, let's see, A should be 3 times bigger than B. So if A is not 3 times bigger than B, 3 times bigger than 2 would be 6. It looks like I'm going to have a limiting reactant of A. What did I say down here? Oh, well, I didn't explain why, but I just explained it verbally. That's a good thought question. It's sort of a qualitative question. You do need to take 3 times 2, but that's easy. In any case, think about it. Chemicals X and Y are gases. They react to form a gas XY, but it takes a bit of time for the reaction to occur. Both X and Y are put into a container with a piston free to move. We're assuming pressure and temperature constant? Oh yeah, so that's why the piston moves, and you note the volume as the reaction occurs. What happens to the volume of the container? I don't know. Let me write an equation. X plus Y, 1x plus 1y. Oh yeah, if Avogadro would say if 1 unit of X reacts with 1 unit of Y and they're both gases and the product is a single gas, then there's only 1 unit of gas over here, and so the volume actually decreases. This 1 liter, say, and this 1 liter react to give 1 liter, which is bizarre. The volume would actually shrink as the reaction proceeds. Believe it or not, I've seen this in the lab. I've tried to do a demonstration. It didn't work out, but I did notice the volume shrinking. Very curious. What does it mean to say one reactant is in excess? Well, all we mean by excess is a lot of it, extra, plenty of it. Sometimes in a limiting reactant, sometimes in a stoichiometric reaction, we'll say one's limiting and one's excess, or sometimes we'll say we have a certain mass of reactant with excess other junk. So the excess just means you don't have to worry about it in your stoichiometry because you have plenty of it. But the other one probably is limiting, but indeed always the limiting reactant is the one that determines how much product I get. Why is the theoretical yield for a reaction? What is it, and how does it depend on the limiting reactant? Well, it's all stoichiometry. The limiting reactant limits how much of product you get, so the theoretical yield is via stoichiometry how much you expect from what you have to work with. Well, that's what I said here, more or less. Yep. Hemoglobin. I know this just seems random, right? But I just snipped some good questions from the back of the chapter. They're good stoichiometry questions. Hemoglobin, 0.347% iron by mass. Each hemoglobin molecule contains 4 iron atoms. Calculate the molar mass of what? That seems hard. Well, I don't know. What did I do down here? I said, let me say 4 iron atoms comprises 0.347% of the total molar mass. Tricky. Nice. So 4 iron atoms weighs this, and the molar mass is unknown, but I know that this 4 iron atoms is 0.347% of the total molar mass. Whoa, hemoglobin's huge. Check it out. 64,000 grams per mole. It's this ginormous, twisted, multi-ribbon, multi-component protein that we need, of course, in our red blood cells. I think the oxygen and carbon dioxide are trapped right here and transport to and from tissues. Pretty amazing. Given the empirical formula, give the empirical formula. This looks like N2O4. This looks like C3H6, I believe. So in other words, these molecules are put together with mutually covalent bonding and a certain kind of atoms, but does that sometimes divide into a simpler number? Molecular formula, empirical formula divided by 2, molecular formula, empirical formula, C3H6, the C3 and the 6 both divide by 2. P4O10, both divide by 2. And yeah, fun, interesting. The most common form of nylon, nylon 6, is 63.68% carbon, a little nitrogen, a little hydrogen, a little oxygen. Find the empirical formula, or in other words, how many hydrogen atoms. I did this as a clicker once. But you remember the trick? Change percent to grams straight away, change the grams to moles, compare each mole to the smallest number of moles, and it gives you one of these, and about one of these, and about 6 of these, and about 11 of those. So in other words, the formula is C6H11NO. I know I'm speaking quickly, I'm talking too fast, but that's the confusion or joy of a video. I can just talk to the video and you'll have to ask me questions or ask your TA questions later. And you can always pause and rewind and go back and look at the PDF. Acetonite trial, starting material for synthetic fabrics and carpets. Here's the equation, 15 grams of C6H6, 10 grams of O2. Oh my goodness. They're giving us not one, not two, but 3 amounts of reactants. And we're supposed to find what's the limiting reactant and how much I would expect. Oh Lord. This one's fun. So, let's see. So let me change grams of C6H6 to moles, grams of O2 to moles, grams of NH3 to moles, then say I need 3 to 2 to 2 ratio. So O2 should, this oxygen should be 3 times bigger than the other ones. Is this one 3 times? No, it should be 3 halves as big as this one and this one. Is this number 3 halves, in other words, 1.5 times larger than this, and 1.5 times larger than this? And the answer is no, it's not. So, because of that, I called oxygen limiting, and I did a little stoichiometry here to find out how much C3H3N I would make. Just a 2 to 3 ratio. It's a 3 to 2 ratio. Interesting. Excuse me, sorry about that. Consider the following reaction. I have a solid and a gas creating a solid. If it takes 2 liters of pure oxygen to react completely with a certain amount of aluminum, what's the mass of aluminum? I feel PV equals nRT coming on here somehow. Standard temperature and pressure, standard temperature, standard pressure. Yeah, I think I'm going to have to use PV equals nRT. So the amount of oxygen that I have is 2 liters, and I have a standard temperature and a standard pressure. That converts via PV equals nRT, chapter 7, on gases, into this one. And then, if that is the amount of oxygen I have, how much aluminum would I be able to react with it? Voila! Convert moles of O2 to moles of aluminum, convert moles of aluminum to grams of aluminum. Simple? No, but straightforward? Maybe, if you know what to do. Consider the reaction: 50 milliliters of methanol with 22.8 liters of oxygen. The products are carbon dioxide and water. Calculate the number of moles of water formed in the reaction. I'm a little bit worried here. This could be a limiting reactant. Dang. Because I have an amount of alcohol with the density and something about a PV equals nRT with the oxygen, so I can figure out the number of moles of oxygen. Anyway, here's a balanced equation. The steps I went through to find the balanced equation with the alcohol, oxygen, carbon dioxide, and water. The milliliters of alcohol changed to grams of alcohol and change grams to moles of alcohol. PV equals nRT gives me the number of moles of oxygen. It looks like I need 3 halves more oxygen than alcohol. Is this number 3 halves more than this one? Oh geez, I don't know. That's tricky. Let me see. What's 1.85 moles of O2, moles of methanol? So in other words, 1.85 moles of oxygen will react with 1.23 moles of alcohol. Do I have 1.23 moles of alcohol? Yes, and more. So I guess alcohol is excess and oxygen is limiting. And then I could go from there to find out how much water. Yeah. You know, I think I've rambled far enough. I've got a few more slides, but I'm tired of talking, and you can watch or look at more PDF slides if you want. And yeah, like I said, we could go on until the cows come home. That's a figure of speech. See you in class. Take care.